So in my lecture, I'd like to highlight a couple of more or less recent developments through which Kraton contributes to circular plastics industry. Was nice to see a couple of things that I'm touching upon as well. For instance, Professor Haji Christidis, he talked about the control of polymers at the molecular level. Of course, in a much more advanced manner through things that would maybe not work in industry at the moment, but maybe could work in future. But this is certainly something that we do as well in industry. But yeah, of course, at a more scalable approach. And then Professor Venneman, he gave a nice overview of TPEs, their use and their technology and application. So I can skip a little bit of my introduction because of that. And actually, I would like to add that the world's largest tire manufacturer is actually using TPEs for their tire, but they're quite small because it's Lego. But I think that's a nice gimmick I always want to mention. It's the largest by number of tires, not by volume of tires, of course. Just a brief introduction on Kraton. We're a global specialty chemicals company. Kraton actually consists of two business divisions. One of them is focusing on pine chemicals, and you find those chemicals actually also in the rubber industry. For instance, we have some pretty nice thread enhancement additives based on pine chemistry. Much of that chemistry is bio-based. I'm from the polymer side, which is unfortunately not much bio-based yet, but that's of course something that we are working on. But we have our sustainability focused programs, and we do contribute to a more sustainable plastic and rubber industry, as I will show in my presentation. Revenue is a little bit less than 2 billion. So we're kind of a small multinational, but I think we're one of the more innovative ones in this field. We spend quite a bit on innovation, have a strong patent portfolio. We have in every region we have some R&D activity. So myself, I'm responsible for our activities for the specialty polymers business in Amsterdam. We have labs in Houston as well as in China, and some smaller R&D centers in India, Japan, and Brazil. We collaborate in the consortium of Together for Sustainability. That's a collaboration between various corporates to align on the sustainability objectives, as they were also defined by the United Nations. And actually, as part of our sustainability effort, we look at making our business more sustainable, and that was certified with an EcoVadis Platinum license. So we're actually in the top tier of sustainable companies. This APR logo and the Plastics Recycling Awards Europe refers to one of the things that I'll come to later. It's about recyclability of our polymers and about their use in upcycling of recycling streams. Just a brief introduction to styrenic blocker polymers. I think you have seen this image. It's just a little bit different, but I think it's important to maybe reiterate, because I'll come back to quite a few of these aspects throughout my talk. We make styrenic blocker polymers, which means that in this case it's a tri-block, and as you will see in a later slide, there's more designs possible. It's a blocker polymer consisting of a styrene block, a rubber block, which can be isoprene or butadiene based in our case, and another styrene block. And you have a physical cross-linking mechanism through the styrene blocks, which is driven by incompatibility, chemical incompatibility with the rubber, but also, of course, by a thermal effect of the styrenes having much higher TG, so they basically separate out also as a temperature effect. So they form amorphous domains, which give these physical crosslinks, which are of course reversible, because if you raise temperature, you take them apart at some point, and actually if you also put on shear, as you do in an extrusion process or in injection molding, you even take out more of that, and that is one of the key driving mechanisms in some of the situations where our polymers work so well. Then there's the other phase of the soft segment, so the rubber mid blocks. They are soft and flexible. They have low TGs depending on the chemical nature. So if you have a butadiene-based mid block, it's like -90 degrees roughly. Isoprene-based is about -60 degrees, and then you can hydrogenate them, and that's actually when we call our polymers specialty polymers. We have those are the hydrogenated styrenic blocker polymers. Of course, they have the benefit of higher stability, both thermal, UV, and some other aspects, but you also increase the TG a little bit. Those are also the parts of the polymer that are oilable. So in a typical TPES compound, as you would call it, there's some oil added, and that is where the oil is and acts as a plasticizer. So that is typically a regular mineral oil. So as I said, we have in our production, so we can actually make our styrenic blocker polymers in various ways, and it's all done through anionic polymerization. That's, I think, why there's still a relatively low number of companies doing this, because it takes some quite significant safety measures. So you can start making a die block and then couple it to a tri block, or you can make it sequentially. If you start making a die block, you can also couple it through various chemical coupling mechanisms and make radial polymers or even star polymers. So there's various design possibilities here, and of course you can combine the different designs if you want to reach certain properties. One of the key things that I touched upon already a little bit is the rheology of styrenic blocker polymers, and the key thing here is that our polymers are very shear sensitive. So if you work at a certain temperature, so for instance, I'm showing the melt viscosity here at 200 degrees. If you increase shear, the effect of shear is much higher than for instance, a polystyrene homopolymer or a polypropylene homopolymer. You see a 5 MFR, so melt flow rate polyprop. We do actually give our polymers melt flow rates, but they can sometimes be misleading, because if you put more shear, it flows actually a lot better. So sometimes you see some of our polymers which have a fairly low melt flow rate, and they actually, if you use them in an extrusion or an injection molding process, and you put on a shear of like 1,000 or even higher, you can actually process it, and it flows pretty well. So if you look at also the melt viscosity, depending on molding temperature, it's a fairly flat curve. So it also gives some processing robustness if you compare it to, for instance, just a polypropylene. Well, most of the styrenic blocker polymers are not used as such. It's actually quite rare that people use a pure styrenic blocker polymer. Typically, they're used in a compound, or they're used in well, as a modifier in a hard plastic, and then you're looking at impact modification. So a typical compound would consist of a styrenic blocker polymer, an oil, and a polypropylene, and you can, of course, add all kinds of additional components like fillers or even some functional materials. We would actually, in our company, we always talk about a GOP compound, so it's a Kraton G oil polypropylene, and depending on the ratio of the different components, you get a different kind of morphology or micromorphology. So And what you're often looking for is an interpenetrating network because it gives a good combination of the two properties. But sometimes, of course, you're also looking to be a bit on the extreme side and have one component in the other. If you would take out completely the polypropylene, you get an oil gel, and those are also, they're pretty solid materials. So you would have like an 20% of styrenic block copolymer typically, and then the rest is mineral oil, and those are all kinds of gel cushionings. There's actually some examples in the US where there's gel mattresses being made out of this kind of material, but you can think of anything that looks and feels like a gel. You can make it from this. The nice thing of these phase structures is if you tune them correctly, they're pretty stable. So they're stable for weeks at 200 degrees. Once you have them and you don't put them in the shear, they're stable. And here you can see some micrographs, as I showed before as well, some transmission electron microscopy. You can visualize it quite nicely. If you take the right staining method, you can color the styrene domains, and the others, the rest will look lighter. Well, just briefly, how are styrenic block polymers applied? It's a pretty broad range of hardnesses. So you start with Shore 00, and that's more like the gel world. So shoe soles, toys, cushions, etc. Even if you take dye blocks, it's used in oil modification and in cosmetics, for instance. Also, tri-blocks are used in cosmetics, by the way, as for instance, depilatory waxes, because they give some strength to a wax, and you can basically, you have some more cohesive strength through the tri-block network. There's the soft touch world, and these are typically like handles of things, whatever tools, but also, for instance, toothbrushes. But it can also be, well, basically any grips or seals, but also hoses. And these hoses I'll come to as well as an example for PVC replacement. And you could also look at replacing silicones for recyclability reasons. And then there's plastic modification. You can add Kraton to various types of plastics, and Circular Plus is an example of that. I'll cover that briefly as well. Well, first example is looking at high transparency flexible compounds for PVC replacement. This is work that was built up, I think, between 1 and 2 decades ago, but you still see quite a bit of traction from the market because PVC remains a material of concern in some applications. And in this example, I'm looking specifically for medical. For instance, there was this request from Swedish hospitals, and they are quite remote. They need to burn their hospital waste locally. And if you do it at too low temperature with PVCs, you get all kinds of compounds of substances of concern out. So they had to get rid of it. Moreover, PVC, there's some other issues as well. And then we're talking about specifically hoses in medical use, but also, for instance, blood bags or IV bags. Well, PVC is a brilliant material, right? Because it's you can make it transparent, you can make it very nice and soft and flexible if you add enough plasticizers. But there's some concerns. There's the concerns end of life. There's also the concerns of the plasticizers, although they've overcome quite some of the concerns around the phthalates. But anyway, as Kraton, we thought it would be worthwhile making an alternative for that. And we made one, and we did it actually through an enhanced rubber segment. So we redesigned the rubber segment of our styrenic block copolymers to meet better the requirements for transparent, flexible compounds. So the enhanced rubber segment, the key thing there is that we increase the amount of vinyl. So if it's a butadiene-based rubber polymer, and you can, as you probably know, you can polymerize that in a 1,4 way or in a 1,2 way. And in the latter case, you get more vinyls. And then, of course, you hydrogenate them in this case, but well, within the company, we call it high vinyl. So you have more branching, basically. It's like a short chain branching. And that gives a very soft material. So it also increases the melt flow of the polymer. So it helps processing. And it's getting softer, so you can do without plasticizers, which is of course good news if you want to look at medical applications where you don't want extractables. Moreover, the compatibility with polypropylene is better, and through this higher compatibility, you get clearer compounds. Of course, it's nice that it's thermoplastic and recyclable. That used to be a non-issue in medical because they would burn it anyway for biohazard reasons. But recently, there's also an uptake in the medical industry that they want to look at recycling their plastics. So there's all kinds of applications for this, but of course, well, this is more of a scientific audience, so you're more interested in looking at the transmission electron microscopy images. So these are two examples. So the top one is an G1650 with polypropylene, a 50-50 mix, and it's showing basically dark stained are the polystyrene domains. So it's showing the size of the domains of the polystyrene. So these are polystyrene-rich domains. So you see that they are pretty coarse. Now, if you take a G1642, which is an ERS grade polymer, you see that there's a much finer network here, much finer interpenetrating network. This is, of course, good news. If you have a difference in refractive index between materials that you blend, you get all kinds of scatter effects. But if the domains are very small, those scatter effects are less. So the good news is that you can make very nice transparent compounds here. Why is this working? Well, there's actually two reasons why this is working. It's a matter of property matching. And on the left, you see an image showing the thermal properties of the rubber block as measured by DMA. And by increasing the vinyl percentage, or actually to be chemically correct, the butylene percentage, you bring together the rubber TG, which is on the lower side, and the amorphous phase TG of the mid block, and you bring it together to 1 TG, which actually matches the TG of polypropylene fairly well. So that's one reason for compatibility. Moreover, there's also chemical compatibility, and this was mentioned before as well. The matching in solubility parameter. The better the match in solubility parameter, the smaller the phase size. So that also helps. Now, getting smaller particles, that can of course be done by putting a lot of energy in. So through your increasing the shear of your processing, but you would get far less stable systems. So once you apply shear again, you may lose that kind of behavior because you have a basically kinetically frozen equilibrium, and it's not really the thermodynamically advantageous state. All right, another example, and this is a recent one that we're pretty proud of, and we are pretty proud of it because we put a lot of effort in it, and this one commercialized quite recently with actually the first commercial car driving around in China with our technology in. This was developed by Kraton with various partners over time in the last roughly 10 years. So it has cost a lot of effort and investment, but I think we achieved something really nice, and I think it's a landmark in the car industry in their lookout for lighter weight and better circularity. So IMSS, it's a trademarked name. It stands for injection molded soft skin. Some of the luxurious cars, they have this very nice soft touch instrument panel. And Normally, the current standard is PVC slush molding, or in some cases, I think they also use EPDM, but it's mostly PVC. That's something the automotive industry is worried about because they want to get rid of it for recyclability and for also for reasons of weight, because PVC is heavier than a TPE compound. So we developed a technology that can produce such skins by ordinary injection molding machine. It's a huge panel. So actually, the art of injection molding is really important here, and it's a very thin wall application. So it's quite unordinary for an injection molding application. So we started with basically, if you look at from polymer to car, what you start with is an HSBC polymer. You compound it. You take the compound. It's injection molded by a tier 1 supplier who makes the instrument panel skin. And then actually there's another tier 1 in some cases who add the backing of that skin, and then it goes to the automotive company. And you need to get all partners aligned. So that's one of the typical examples in industry, getting people aligned. We spend a lot of time talking to get people aligned, and much less time on the real science compared to what you're doing. Anyway, there are significant technical challenges. As you can imagine, having an instrument panel, and you know dashboards in cars, they're big. You need to have your polymer match those dimensions, and you need to make sure that there's enough flow, so you're reaching also the interestingly shaped corners of this instrument panel. And we put the requirement of that there's no special injection molding machine needed, because we didn't see tier 1s invest millions and millions into a new injection molding machine. As a matter of fact, and just the mold is already around $1 million investment. So that's already significant enough. So we had to develop high flow HSBC polymers, and that's what we did. And in the end, the result is basically, and I'm looking at sustainability here. We actually got nominated for an ERJ top 10 award. And actually, the outcome is that you can save weight on your vehicle. There's improved aging and fogging and VOC and odor performance because it's phthalate-free and low plasticizer. In some cases, we reached an improved abrasion and heat resistance, and it's thermoplastic, which is of course helping recyclability. Now, of course, you're curious about the technology behind this, and the technology is all in rheology, and we contribute part of this, and our compounding customers contribute the other part. So this is all about the rheology of the HSBC we're using, and these are two chemically comparable HSBCs in the dotted line. So G1643 is an ERS grade Kraton, and you see the curve here in orange. And if you redesign that polymer, and that's a combination of styrene block size, molecular weight, etc., you can significantly reduce the shear viscosity. So depending on shear, you get a much better flow. And this is of course helping injection molding in this region, which is the typical shear rate in injection molding. And now if you make a compound, and the green line is giving a classical Kraton G-based compound, and the blue one, and a compound that was developed for IMSS, you can even reduce this a bit more. And by tuning this viscosity at a certain shear range, you can reach the long flow paths that are needed for such a large object and with such thin walls. Of course, there's an awful lot of other properties that you need to test, and we did all that: heat, aging, scuff, mar, weathering. There's well, you wouldn't think of it initially, at least I didn't, but one of the key aspects is airbag deployment. If an airbag deploys in an accident, you don't want pieces to be flying around, so things need to tear open properly, but still need to stay together. It's all that kind of properties that you need to think of. And there the polymer design is key, but it's only it's still a fairly small part of the total picture. Last topic for today, Circular Plus. I'm not sure how much time I have. I think I have like 5 minutes left. Is that correct?
Yes, that's correct.
Okay, good. So you all know that circularity in the plastics industry is a key challenge, right? And we contribute our part to it. And this topic is actually about plastic modification rather than about thermoplastic rubbers. There are some key issues in especially mechanically recycled post-consumer recyclates, but also post-industrial. There's contamination. For instance, if you want a recycled polypropylene, quite often there will be small amounts of polyethylene in there because it's technically difficult and then also economically unfeasible to completely separate them. This leads, there is some incompatibility between those two different types of polymers, which is impacting the mechanical properties. Even worse, if you have contaminants of maybe some biological fibers, metals, etc., it can actually lead to defects. You can never get completely pure polymer streamed out of a recyclate unless, of course, you do chemical recycling, which is one step further and is, well, in some cases, it's the only option. But of course, you want to stay as close as possible to the original polymer structure. So what we can do with our Circular Plus compatibilizers, and we developed them specifically for this market, it is actually based on styrenic block polymer technology, but they are focused on this market. We can stabilize the morphology, we can enhance the properties. That's something we did already because HSBCs are quite often used as an impact modifier in all kinds of plastics. And that balances, of course, with the recycling industry's drive towards pure PCR streams, but we can also actually, in some cases, improve processability. This is an example. Excuse me. This is an example, and we're comparing here with a polyolefin elastomer, because that's a solution we see quite often in the market as well. It's always good to compare with a competitor, and mind you, they're doing a fairly good job. But I think with a styrenic block polymer, you can do better. There's a much stronger balance between the modulus that you want to retain, because you don't want weak objects, you don't want things to bend too easily, and the impact improvement that you can reach. This chart is showing in yellow. It's showing the PCR polypropylene. I believe this was a 95 or maybe 98% pure one, so it's already a fairly pure one. But you see that the impact resistance at room temperature, and especially at low temperature, is not good enough. Now, adding about 9% of the Circular Plus additives increases that impact resistance, but keeps the modulus at a fairly good level. There's also a little bit of impact on the melt flow rate. Well, this is an overview of how our compatibilizers work, and this is actually an example of a soft phase being dispersed in a hard phase matrix, but there's also the compatibilization effect. I think Professor Venneman showed a nice image of small rubber bits in a hard matrix. That's more or less what you have at 9% addition. You start to having those domains, but if you go to a much lower percentage addition, you do have the compatibilization effect. So you do already increase your impact strength quite a bit, but you don't have this significant loss in modulus that you often see when you add more. Depending on the processing conditions, you can choose between the different grades. The C3000 is an unhydrogenated styrenic blocker polymer. C2000 is hydrogenated. It's so that one is a bit more powerful if you, for instance, process polypropylene, because you can go also to a bit higher temperatures. There's another example. This is actually looking at two, well, pretty much completely incompatible streams. This is looking at the compatibilization series, so the C1000 series, and these polymers can actually make the incompatible compatible. So if you take a PCR polypropylene, a PCR PET, and a C1000, you can get pretty good properties, and even combine the two streams, which can be beneficial, and it's showing that you can sometimes live with some contaminants. Well, just very briefly to wrap up, a couple of other sustainable solutions, a little bit outside my direct working scope. We have the highly modified asphalt, which improves pavement performance and reduces maintenance. So it's a styrenic blocker polymer added to bitumen, and it's basically giving elasticity to a road. We have some Silver Road RP1000 performance additive that helps recycling of asphalt. In adhesives, we have our Revolution rosin ester, which has a very high bio-based content as a tackifier. You can enhance the performance through a styrenic blocker polymer technology. And I mentioned already briefly our Silvertrax strand enhancement additives in tire. They help with rolling resistance and grip balance. And there's some core rubber additives that we have as well as processing aids. So thank you very much for your attention. If there are any questions, I'm happy to answer them. If that doesn't work now, feel free to drop me a note